Okay, this begins EE 555 discussion on Wednesday, January 15, 2014.
Okay. Good morning, everybody. Can you hear me? All right. So my name is Angelos Lazaris. I recognize most of you basically from 450. For those that don't know anything about me, I'm going to be your TA, one of the TAs. And today basically I'm going to present some introductory material about some logistics that we need to know for E555, and then we'll see some introductory problems of probability. Okay, feel free to ask questions, to interrupt me, and otherwise I have office hours right after the discussion today, and we can talk also there. So let's quickly go over the logistics. Most of you have seen that. For those who haven't, you can slowly go over it offline if you want. We will quickly go over it because I want to emphasize on the problems today. Okay? So, I'm the first TA. My name is Angelos Lazaris, as I said. This is my email. Feel free to email me whenever you have questions, and if I am your designated TA, as we will see shortly. I'm a PhD student in electrical engineering with emphasis on computer networks. And my office number will be PHC 330, same as 450 for those who took the class. The office hours, they are fixed for now. I don't think there's going to be any change, but in any case, you can use this for now. It's Wednesday 9:30 to 10:30, right after discussion, and Friday from 11 a.m. to noon. The second TA, and this is the office telephone, in case you are remote or you want to talk on the phone, basically. All right. TA number 2. Any questions? No. TA number 2. His name is Nachikitas. You can call him Nachi, I guess. He will introduce himself soon. He will be back maybe in 1-2 weeks, and his email is given here. He's a PhD student also in electrical engineering with emphasis on computer networks. Same thing, same office. Office hours will be announced. Okay? All right, so quickly, what are our responsibilities? We'll conduct weekly discussion sessions. Most likely there's going to be a second discussion session, but this is not, fixed yet. So the professor will talk about it. We want to, to make you be flexible and to have the option basically to come to another discussion session if you cannot attend the morning one. One of our responsibilities is to maintain the course website, and we'll be conducting office hours which are open to everybody. Okay, so whenever you can come to any one of the two of us and come with questions. We'll be designing and grading basically homeworks. It's not about projects here. This is, it's not fixed yet about this point. And then we'll be assisting you via email, and basically, irrespective of which discussion session you attend, you can just email us and email basically the one that is your designated TA, as I said. We have the same policy as in 450. And what this means is that you will be divided in 2 groups. Since we are 2 TAs, one TA is going to be assigned to you, and you are going to be emailing this TA and only this TA through email. Okay? If you want to meet somebody in person, feel free to go in the office hours to any of us. and that's perfectly fine. So if you don't email, the designated TA will be forward the email to the other TA. We are two. We don't, have a big, anyway, set of TAs here. And also, the course website, for now, this class is going to be on DEN, since I don't think this is going to change, but in case it changes, we're going to become a Blackboard class. But for now, you will use this class, this website here, USC DEN. Nothing really new, right? You know these things. And all the material will be posted there. And please read your emails often, because we'll be announcing homeworks, we'll be announcing, grades posted and things like this over email. All the communications are going to be based on that. And we assume that you read your emails on a daily basis. There's going to be 5 to 6 homework assignments. The professor will talk more about that, over the course of the semester. And the submission of the assignment is the same as in 450. You are going to turn it in class. For the DEN students, they have some half extra day. They can return it the day after the announced due date, basically at noon, before noon. Okay, so the goal of the homework is to make you understand the material, obviously, and just start early on. And don't email us last minute, because it's impossible to answer to so many emails last minute, okay? Just give yourself some time to work on the homework and, come up with questions, and then we'll have the time to answer. All right, so for the grading policy, basically you will have some time to, from the time the grades are posted, we'll be emailing you for that, and you have some time to pick up your homework, okay? You should pick up the homework from the professor's office, and don't leave it there, because there's going to be a penalty if we have like accumulation of homeworks. And the main purpose of that is to make you read the comments of the, that the grader wrote, understand your mistakes, correct your mistakes, and get ready for the exams, okay? Prepare. So you'll have 2 weeks to react from the time we post the email, from the time we broadcast the email, and if you have grading issues, feel free to email the grader. So basically what happens is that when you get your graded homework assignment, there's going to be the initials of the grader in the first page of the graded assignment. So you'll go to the DEN website, in the staff information, you'll find who the grader is, you'll match the initials, and you're going to email this grader, okay, if you have grading questions. So you have 2 weeks to react, and whenever you do that, you should email the professor and your designated TA. Says that, we're all aware of what's going on. I'm not grading, and the other TA is not grading as well. We have specific, we have graders for that. And those are the ones that are going to solve you, answer to you in any questions you have regarding the grading. The same for remote students. They have 2 weeks to react to that, and they should pick up their assignments through DEN. This is a different issue. You are not, they have, a different procedure because of DEN. Okay, so any questions so far? I guess everything is clear. If you want more information, you can email us. I think everything is in the syllabus so far, in the material that the professor has posted. If you haven't seen that, go to DEN and download all the material, because he will be posting pre-lecture charts that you can review before going to the lectures. And all the material, related to the class basically is posted. Okay, and now, we're going to be posting the discussion notes and also lecture charts and everything. Okay, so after this quick introduction, let's go to some probability problems. All of you have taken 450 or 503, right? Sorry, 465 or 503, meaning probabilistic modeling. So we expect that you have seen the basics at least, and you are able to quickly review the material and understand what we are writing here. Sometimes the derivations are not going to be really detailed. Today we're going to be really detailed because it's a introductory discussion. So we have simple problems, I guess, but sometimes we assume that you understand the steps that we follow. Okay, so let's see the first problem here. Can you see the figure? Yeah, I think it's clear. We have considered the following network as shown in the figure. A message originates with equal probability at either nodes A or B. Okay, so we have a message originating here or here. The final destination of the message is node E. Any intermediate node receiving the message on a link duplicates it on all the other links outgoing from it. For example, if node C here receives the message from anyone, it duplicates it and sends it to node D and E. Okay? If, for example, B sends a message to C, then it's going to be broadcasted to D and E, or multicast if you want. Okay? Alright, so a communication on each link is successful with independent probability P. Some small note here, these problems don't try really to map it to a protocol that you already know. Okay, they are mathematical problems and they might not make sense from the strict protocol perspective. Alright, we're not talking about slots, for example. Here we're not talking about, I don't know, how the notifications are done or how the broadcast is being conducted, these type of things. Okay, it's just an abstract problem, and try to solve it, without really mapping it to a protocol that you know. So, with that said, we said that we have a successful probability of success is P, and this is independent. Okay, we have an independent experiment. So the questions are, given that the message is successfully received at node E, what is the probability that it originated at node A? So we received it here. What is the probability it came from here? What else can have happened? Could have happened? It might be coming from B, and then C and E. It might be coming from B, D, E. It might be coming from both. Many things can happen, okay? So we need to write down all these cases and use probabilistic reasoning to answer to the question. All right, so can we switch to the overhead? All right. Okay. We're going to post all these notes, by the way. So you don't have to, if you feel that you need not to write anything in order to follow, just feel free to follow. Okay, so problem number 1. I'm not going to write down the problem statement. You'll have it in the presentation. So the first question, as we said, is what is if the message is received at the destination, what is the probability it came from A? For that, we'll define the events in our problem, and then we'll use these events, the probability of these events, to calculate the probability we want. All right, so let A be the event. For example, this is very low level. We define all the events carefully and things like this. You might not have the time to do that. So just we assume that, okay, we know what PA is. Okay, so let A be the event that the message was sent by A. We all understand that, okay? Also, similarly, let B be the event that the message was sent by B. Clear? And we can, of course, define the probability, event C, D, E, being the event that the message was received by one of these nodes. But in our case, we can also go straight and define some composite events that I'm going to tell you now. Because in any case, if we need it, we're going to define it later. Okay? For now, let's define a few more events. Let CD be the event the message was received by C and D. Okay? And similarly, we are going to denote as the complement of a set of an event. We're going to denote it with a star, C star, D. What's that? The message wasn't received by C, but it was received by D. Okay? Message received by, not received by C, but received by D. And then we'll define also similarly CD star received by C but not by D. What else we have? We have C star, D star. Neither C nor D received the message. Is it clear? Okay. So with that said, why we define these events? Because we're going to use those events later for our analysis. I guess it's better to do it at the beginning. So we want to calculate the probability of A given E. What is E? And let's define also E. The event, the message was received by E. Okay, so probability of A given E, how can we calculate that? We have, let me use this because it's easier from switching back and forth. We have this being the destination. We want to calculate the probability that we receive E if, the probability it was sent by A if we received it at the destination. Okay? What is the first tool that you would use from 465 or 503? Any ideas? Louder? Bayes rule. Okay, we can reverse the conditioning, okay? Actually, even if you are not sure that this is going to work, just try it out. It's the first and easiest thing that you can do. Okay, so according to Bayes, I'm writing down what's the intermediate step, why we use the formula, but you'll be able to, I guess, to understand that even if we don't say it. Okay, so according to Bayes, we can change the conditioning here, the sequence, and we have probability of phi given A times probability of A, and what is in the denominator? It should be probability of phi, but we'll use we'll break it down, yeah, using the law of total probability, and this is going to become probability of phi given A times probability of A plus probability of phi given B times probability of B. Okay. However, probability of A equals probability of B equals half by definition. Do you agree? So all these three can be, removed. Okay, so for that equation, what else do we need? So P probability of A given E is going to be P E given A over P E given A plus P E given B. Let's see, can we calculate those guys? From what do we know? We know that probability of E given A is, what is the probability we receive it here given that it was sent by A? No, we said that we have probability of success P. So this probability will be, do you agree? Look, here we have a communication on each link is successful with independent probability P. So P E given A is equal to P, if we know that A sent the message. Do you agree? Okay. So we know those two terms. We want to calculate the PE given B now. So for that part, PE given B, as you see here, given that it was sent by B, many things can happen. So we have another next step here. So if you remember, what we do is we condition on what can happen. Or you can just go directly and apply the so-called law of total probability and calculate this probability, the probability of E given B, by conditioning on a partition of the sample space. That's what it is, which means that we will find disjoint events that they can partition the sample space in, with no overlap, meaning those events, and then we can condition on that and find the probability. Okay? So let's apply that from law of total probability. If you don't remember these things, go to the book 465 or 503 and review the material. So what do we have over here? We have probability of phi given B. So what we need to condition on is those 4 events defined up here that create a partition of the sample space. Do you agree? If we take the probability of all those 4 guys, then it's 1, right? And if 1 happens, the other doesn't happen. Okay, so with that said, over here we have probability of phi. Look what happens here. We have the law of total probability, if you remember, but we have a conditioning already. So we will use the more advanced version of the law of total probability, which uses conditioning. And this, I think you have seen that in your probability class, right? So what happens here is this is going to be probability of E given B, comma CD. If this can happen, have happened, meaning if the message was received by C and D, times the probability of CD given B. We always have given B here. That's the only addition from the simple law of total probability that you know. Do you agree with that? The next is, what is the next term? Probability of phi given B, of course, and then something else like C star D times probability C star D given B plus probability of phi given B, comma C D star P C D star given B plus, I'm going to write it here, probability of E given B, C star D star P C star D star given B. Do you agree? Is everything fine, guys? Okay. So what can we calculate from here? First of all, let's go to this event over here, which is easy to calculate, the last one. The probability of E given B, and that given that B sent the message, what is the probability we receive the message given that it was sent by B and not received by C and D? Over here. If it's not received by C or D and D, then it's impossible to be received at the destination. So the probability is 0. Right? So with that said, probability of phi given B, comma, C star, D star is 0. Okay, so this thing vanishes from here. We have another probability which is probability of E. Now we have to calculate this basically. E given B, C star D times probability of C star D given B. I'm going to claim symmetry here. Do you think that the problem is symmetric? So the probability of if one of the two received the message, it's the same, right? If one versus the other. So I'm going to write here that this is equal to probability of E given B, comma, C D star times probability C D star given B. And now let's calculate this. We have probability E given that it was sent by B and received by C and not D. So what happens? We have, as we said, the minute somebody receives a message, broadcasts. Okay? So if the message was received by this guy and not by this guy, what can happen? Either it was sent successfully from here, it wasn't successful from here, and it wasn't successful from here. Or it was successful from, can it be like go to D and then to C and not to D? No. We contradict ourselves. So D didn't receive the message from B. Okay? So it can go, basically we have this only case. The probability that it goes from B to C straight is how much? P. So this is P times the probability that at the same time D should not receive the message both from B and C. And this can happen with probability how much? 1 minus P times 1 minus P. So 1 minus P times 1 minus P. For your convenience, and since we are trying to warming up probability reasoning, I'm going to explain why this happens. This is from B to C, assuming that C received the message. Okay, in this equation here. B to C, this is from B to D, and this is from C to D. You understand what I mean by that, eh? Okay, so we have all the cases here, and what else? And that's it. So now we calculated this probability. It's basically, okay, let's rewrite 1 minus P squared. The other probability is the probability PE given B, comma CD. That's the third case we have. And times probability CD given B. How much is that now? What does this mean? This means that we received the message at E, it was sent by B, given that it was sent by B and received by both C and D. So many things can happen. Okay? In cases many things can happen and it's hard to enumerate, we usually take the complement. We say 1 minus this didn't happen. Otherwise you have to sum up all the events. Here it's not a lot, it's just 3 events, but you can try both at home. What I mean by that, the probability of received by E, given that it's sent by B and received by CD is what? 1 minus it wasn't received by both C and D. Do you agree? 1 minus P squared. And the probability, and this also is equal to, I'm not going to write that, it's going to be confusing. You can break it down by P, 1 minus P, P, and P squared. Those are the cases, either one of the two received the message and then broadcasts, and so both have the message. Okay, so then PCD given B is what? The message was received by C and D given it was sent by B. How many cases we have here? One is it was received by C, yes. Assuming that C received the message, probability C receives the message is P. Okay? If D didn't receive the message in the first transmission, this can happen with probability 1 minus P, and then it receives the message from C. Right? Message goes here, this guy doesn't get the message from B, but it gets the message from C. The probability of that is P, 1 minus P times P. Plus, the message goes to D with probability P. It doesn't go to C from B, but it goes to C from D. Same probability. P, 1 minus P times P. Plus, the message goes to both of them directly. Both C and D get the message directly from B. This can happen with probability P squared. Now, do you have any questions now for that? Should I condition further on what's going on? If this message broadcasts and if it's received or not received in all these cases? We should have a partition of the sample space, meaning all the events covered, right? It is all the events covered, but if we condition further, we're going to end up with 1. Because we take all the subsequent cases, right? Meaning if C received the message and then broadcast or didn't broadcast, no, received by D from C or not received by D, it's not going to affect anything. C has the message already, so, right? We can just ignore that. So what else do we have here? I guess that's it. We can do the calculations now. 1 minus P squared. And here it's 2P squared 1 minus P plus P squared. Okay? So let's continue on that. With that said, PA given E becomes P. I'm going to just add all these probabilities together, and you're going to do the math at home because we want to see the other problems. 1 minus P squared plus 1 minus P squared plus 2P squared 1 minus P. Okay, and this gives 1 over 1 plus 2P 2P squared minus 3P to the power of 3 plus 2P4. Okay, this is just algebraic calculations. You can do it at home, I guess. Are you okay with that? Any questions? Okay. So the second question here is, what is the probability the message was sent by B given that it wasn't received by E? Okay, for that, what do we need to calculate? Let's use base again. P E star given B times PB, P E star given B times PB plus P E star given A times PA. Okay, this is straight from base rule. From that, what can we calculate? We can calculate P probability of probability of E star given A. Probability of E star given A is probability that we didn't receive at E, given that it was sent by A. This is 1 minus P. Probability of E star given B is equal to what? It's complicated, but we have calculated the complement of this event. So we can write it down as P probability of E given B. Why? Because we have this probability calculated up here somewhere. Okay, here. Probability of E given B. You can sum up all these terms and find this probability. And probability of A equals probability of B equals half. We know that. Alright, so if we put all this together, now it's just algebra because we know everything. We get probability of E given E star, B given E star is equal to, this is a huge equation here, 1 minus 1 minus 1 minus P squared plus 2P squared 1 minus P minus 2P squared 1 minus P squared. And here it's 1 minus this guy, that's 1 minus P squared 2P squared 1 minus P minus 2P squared 1 minus P squared plus 1 minus P. Okay? And this gives, if we simplify, 1 minus 2P squared minus 2P third plus 5P fourth minus 2P fifth, 2 minus P, 2P squared, 2P to the power of 3, 5P4, 2P5. Okay, so, are we okay with that? Any questions, guys? All right. Can we go back to the overhead? Okay, so let's continue to the other problem. We have the following hammock network. This is how it's called because of the form that the network has. Switches are independent, each closed with probability P. Okay, what is the probability that A can communicate with B? We have 2 points, A and B. When this communication is possible, assume that we have a probabilistic switch. It's on or off with probability P. Okay, we want to find the probability that we can communicate from A to B, meaning there is a path that goes from A to B. Now this expression, there is a path, means many things because it's a combinatorial problem here, right? So usually in these cases we take the 1 minus, it's impossible to communicate. All right? So let's see how we can solve this. Problem 2. Can we go back to the overhead? Sorry, to the, overhead. I'm right. Okay, so I'm gonna use my scratch paper. Okay, so here we have the this network. We said that we want to go from A to B. Let's narrow down and calculate all the probabilities that we know so far. And be careful by saying a switch is closed, meaning the contact is down, so traffic can go through. Okay, this is called closed, not turned off. So probability switch is closed is what? We know that from the problem, it's P. Okay? Probability switch is open is equal to 1 minus P. Probability look at the form of this. We call this stage. Okay, first stage, second, so on and so forth. Each stage, it has L switches. Okay? What is the probability all switches in a stage are open? Open meaning no traffic can go through. Because what we're trying to calculate is break down the problem of communication end-to-end to the communication that there is, some breakpoint. Okay? Traffic cannot go through in some stage, or more stages, of course. So probability, all L switches in a stage are open is what? To the power of L, right? Correct. It's 1 minus P to the power of L. We have independent switches. We said we can multiply, take the product rule, multiply the probabilities. Perfect. So now what is the probability each stage is closed? Closed, what do you mean by each stage is closed? We focus on a given state. What is the probability traffic can go through? Look at how it's formed. Those things, if a path exists here and we receive path here, traffic here, it can go down and go like this, right? Because those are connected vertically. So it's enough, if we want to calculate the probability, each stage is closed. What is that? We can say 1 minus the probability is open, right? It's easier because many things can happen. So probability, each stage is closed, is 1 minus P to the power of L, the probability above. Do you agree? So finally, probability, all stages are closed, which means we cannot, we can communicate. All stages closed, meaning we have a path here, 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 and here, everywhere. That's what I mean. Closed meaning there is a path, right? So the probability each stage is closed is what? We have k steps independently, we multiply. The probability, the individual probability is this one. Do you agree? So this is 1 minus P to the power of L and all to the power of K. And this is equal to the probability P network closed, as we say, which means i.e. there is a path from A to B. Okay? Any questions? Okay, good. I'm telling you the most important point here, because if you read it again it might be confusing, is to understand the difference between closed and open. And by closed we mean contact is down, we have traffic going through the switch. Okay? Alright. So let's continue with the last problem. Can we go back to the presentation? Okay. So the third problem, we have this topology shown in the figure. Consider the following network. Host A transmits a message to host B. There are two routers in the path between A and B, denoted as R here. The probability that a router receives the message in error is P. Now we have probability of error, P. A router will drop the message if it detects to be in error. If either router drops the message, the source host will transmit the message. Transmit means successfully, it's going to go through. Both the host router and router-router links are counted as hops. So a hop is this link here, this line here, and this line here. We'll have total of 3 hops. Why we say that? Because we'll use it in the questions. The first question is, first of all, the question does not pertain to an actual protocol. It is just a simple exercise in probability modeling, okay? So meaning we can assume that we have a magic acknowledgement. If somebody receives a message, we know at the center that message was received. Okay. So the first question is, let X be the number of hops the message makes per transmission. Find the average value of x. Note that x has nothing to do with reception. What does this mean? X is the number of hops per transmission. A transmission is an effort to send the message. What can happen? It can be dropped at the first link, it can be dropped at the second or at the third. If it's not at the third, yeah, at the third as well, and then go back, right? So we want to count the average of this x, which is on average how many hops it's going to do in order to reach the destination, okay? Per transmission bit, basically. Okay, let's write this down. Can we go back to the overhead again? Thank you. Problem 3, we have the simple topology here. Okay, so what are the values that x can take? X can take value 1 clearly, right? We can have 1 hop per transmission, and when this happens, if the message is dropped at the first router. So we have x equals 1 with probability, how much? The message was lost here with probability p. We can have 2 hops if the message goes first successfully here and then it's getting lost here. This probability is p, let's be like 1 minus p times p to make it more clear. And 3, 1, 2, 3 hops when? We have, be careful here, the error we assume it happens at the router, right? So it goes here and then it's dropped, right? So, or basically no, what I want to say is that we have 3 hops when, if it goes here, then here and here, this means it was received. So we have 1 minus p from here and 1 minus p from here. Because only routers drop the packet, right? Those are the end hosts. So this can happen with 1 minus p squared. Do you agree with that? Does it look familiar? So the expectation of x is by definition probability times the value summation, right? So it's 1 times p plus 2 1 minus p times p plus 3 1 minus p squared. That's it. We can leave it like that. Do you agree? Okay. So that's the first question. I guess it's easy. And let's go to the second question, which is let y be the number of transmissions, not the number of hops, just the number of transmissions a message makes until it is received by host B. How many times we need to try in order for the message to be received. And we want to find the average of y. Okay, so y so that's the question here. Let y be the number of transmissions, not the number of hops a message makes until it is received by host B. Find the value of y. So I don't know how you would tackle this problem, but if you remember from 465 or 503, it's very common. It's very common to map this problem to something that you already know. It's a sequence of Bernoulli trials, basically, if you think about it, right? And this sequence of Bernoulli trials creates a geometric experiment, right? Meaning it can be modeled by geometric distribution. Do you agree that we have a geometric distribution here? And if yes, what is the probability of success? What is the geometric, first of all? What does it model? We have a sequence of Bernoulli trials, which means something happens with probability p. This is called the probability of success. For example, what is the number of flips we need to do in order to have a head? If we call probability of head p, then this is a sequence of Bernoulli trials and we have a geometric distribution, right? Okay, same applies here. We need to find the P probability though. So we will use what we calculated above, one part of it. If you think about it, P success here is what? The probability that the message is received at the destination. This can happen with how much probability? 1 minus P squared. Perfect. That's all we need now, right? Is this independent of the next round? It is. So we have a sequence of independent Bernoulli trials with probability of success, P success. So this is Y then, Y is the random variable we defined above, is modeled by a geometric distribution with probability 1 minus P squared. That's how we write it usually, right? GOP. So we can just directly go, instead of calculating summations and all this complicated stuff, we can say we know that the expectation of Y is 1 over P. So expectation of Y is 1 over P success, which is 1 over 1 minus P squared. Yes? The third link, if you see the, good question, if you see the question, we say that the probability that the router receives the message in error is P, the router. The last node is a destination. So the error can happen at the router level, not at the destination. Okay? Do you agree with that? So this means that an error can happen here or here. Yeah, exactly. If it's sent by here, it's going to be received. Do you agree with that? Yeah? Okay, so we can have 3 hops, but the last, yes. Here we won't have an error. Okay, so that's it. If you are okay with the geometric here, I think we are done. Any questions? Okay, we're doing... Okay, thank you guys.
And this concludes EE 555 discussion on Wednesday, January 15th.